So you guys been working on gravitational fields, and now we're going to start moving into what are called electric fields. And electric fields have some similarities and some differences compared to gravity. One of the key differences is gravity, you think about big things, and electric fields are often about little things. Gravitational fields, you think about planets and gravity and stars and some space stuff, and it creates planetary orbits and that type of stuff. And electric fields do a lot of the exact same stuff, except typically at the subatomic level. So for masses, it's often like the big stuff is what people think about when we look at big things falling and big things moving and doing different things. With electric fields, a lot of this is dealing with more at the subatomic level. So we're looking at things like electrons and protons and charges of that type of stuff. And this really leads to things like atomic structure and a whole bunch of other stuff you guys actually did in grade 9 science as well. But we'll just start with some basic type stuff. Just like gravitational fields, we'll sort of map that out first a little bit. You guys, when you guys did your gravity type stuff, you've got a mass, and the mass has a gravitational field. And what happens is, you take another little tiny mass. So here's a little tiny mass, and of course the mass would fall towards the big one. So because of that, we would draw gravitational fields, and we draw them going into it because that's what masses do, is they go towards other masses. We draw gravitational fields going in, even though we know the actual gravitational field actually goes out. Well, we can do the same type of thing with electric fields, except the core quantity for electric fields isn't mass. I'm not really worried about mass with electric fields. It's more about electrical charge. So if you remember from grade 9 science, you're introduced to charge, and the symbol for charge is a Q. And this one you can do like a capital Q or lowercase q. It doesn't really matter too much. It's one of the few things out there that you can go back and forth. Just like mass, you often go back and forth between capital and lowercase. You can do the same thing with charge. And you guys are introduced to charge in grade 9, and this is measured in what are called coulombs. And that is the symbol, or the symbol will be C, and that is the unit for charge. And this also cracks in another major difference between electric fields, magnetic and gravitational fields. For charge, there is positive and there's negative. There's a positive charge and there's negative charge. And for mass and gravity, there's just mass. There's only one kind. So for electrical stuff, a little bit different because there's positives and negatives. So for gravitational fields, there's things always attract. Well, in electric fields, they can attract or repel depending if they're positive and negative. So here we have positive negatives. They can attract and they can repel. And these two things here, those are probably the two biggest differences between the gravitational field stuff you guys have done and the electrical field stuff is the two types of charges and attracting and repelling. So that's where the key differences sort of kick in between the two. Okay, but we're going to start sort of like how we started with gravity, just drawing them out and sort of see what they might actually look like. So we'll do the same type of thing that we did with gravity with electric stuff. Now for electric stuff, it's not mass that we care about, it's charge. So here I'm just going to draw a little charge like this. So there's a little positive charge. Now this thing gives off an electric field. It gives off an electric field all the way around it, just like masses give off a gravitational field. Now, which way do we actually draw it? Do we draw it going in or do we draw it going out? We know it goes out, but which way do we draw it? Well, we draw it based on what it'll do to, say, a little positive charge. And if you have a big positive charge and a little positive charge, that little positive charge is going to be repelled and it will go away from it. And that's why for positive charges, we draw the electric field going away from it, something like that. So that's how we draw electric fields for positive charges. We draw them going out of positives. And the standard color coding for electric fields is red. Now, the same type of thing can be done for a negative charge. If you had a little positive charge close to a negative charge, it would want to go towards it. So since it goes towards it, that's the way we draw electric fields for negative charges. Even though the field actually goes out from the negative, we draw it going in based on what a positive test charge would actually do. So electric fields, and the symbol for electric fields is a capital E, and it is a vector quantity. Electric fields are actually drawn based on a positive charge interaction. And the easiest way to think about it is a proton. If this was a proton right here, it would be repelled by the positive. If this was a proton right here, it'd be attracted to the negative. And that's the way we draw electric fields, based on what a positive charge would actually do. And the same thing is true for when we have combinations of charges. So for example, if we had a positive charge and a negative charge, and we want to draw the electric field between them, well, imagine we had a little tiny positive charge. So there's my little tiny positive charge right there. Grab my selector tool here. And if we want to see what it do, if it was starting over here, it would start at the positive here and whoom, go straight across the negative. If it was over here, it'd be repelled by the positive and move away from it, and then the negative would slowly start pulling it in. Same thing here, it'd be pushed away over here, and the negative would slowly pull it in. And that's the basic idea how we would draw the electric field. It starts the positive and does something like this, because that's what a little positive charge would do. It comes out this way, wraps around, and goes to negative. And it's nice and symmetrical in this one. And even out here, it would wrap all the way around and come back in this way. So that's what we draw for the field, because that's the little positive would do, would scoot across here. It would come out this way, wrap around this way, like this. If we make a bigger diagram, it'd come out like this and loop around and eventually come back over here. So that's the way we draw the electric field between two charges like that. Even if there's two charges that are same charge, like maybe we had a couple of positives, something like that, well, the electric field would actually be drawn something like this, because of course the two positives would repel from each other, they'd push away from each other, something like that, and you can sort of see that electric field interaction between them is what actually caused them to separate. So if we had a little positive charge here, this little positive charge would not want to go to that positive. It would get pushed away from this guy and scoot up this way, or scoot up down this way, or try and get away from it whenever it can, following those field lines. That's what little positive is going to do. Okay, even if you can change shapes, there's lots of different shapes that you can use. One of the more common shapes that is used is to actually use big pieces of metal, like sort of like metal pieces, and I'm going to draw this out a little bit like this, and then sort of think about metal plates. So big metal plates are a really common thing to use, and we'll get to that in just a second. And if we had, often we'll have like one plate will be positively charged and the other plate will be negatively charged, and the electric field would go across the plates. And if you would take this little positive charge and you'd put it inside of here, it's going to start at the positive plate, it would be pushed away from the positive and attract the negative, it would fire straight across. Same thing over here, just fire straight across. That's what it wants to do, is just fire straight across. And that's because the electric field would actually be drawn something like this. And there's electric field on the outside of it as well, but we're more concerned about what's happening on the inside. And this is a really, really, really common thing to use. So let's move that guy out of the way. This is a really common thing to use. This is called a parallel. This is called parallel plate setup. So there's a couple of parallel plates. And the reason this is so common, and it's used for lots and lots of different things, is right inside of here, right in the middle, right inside of here, you get a very, very, very strong electric field. And not only is it strong, it's also nice and uniform. So it's nice and even, the lines are parallel, it works really, really well. And so because of this, you get a nice strong electric field inside, but also it's really, really nice because you get a nice constant force and acceleration inside of there. So it makes it really, really easy and handy for us to do stuff with parallel plates because the forces are nice and strong, they're uniform, nice constant forces, you get constant accelerations. It works really, really nicely. Okay. When you don't have uniform electric fields, things, that's more of a grade 12 thing that we'll look at next year. But for grade 11, we just look at nice little parallel plates and just the nice constant forces that go along, and we can calculate forces on charges inside of parallel plates and stuff like that. Okay, so this is the basic idea behind electric fields. So we got charges, they create we have positive, negative charges that create electric fields. The electric fields do radiate out from all charges, but we draw them based on what would happen to a positive charge. So here, this little positive guy is repelled, so we draw the field going out. This little positive is attracted, so we draw the field going in. And then we have combinations of charges, whether they're point charges like these guys or plates. We draw the field going out of a positive towards a negative, and we just sort of think about what a little charge might do if it was interacting between them. One of the biggest things, though, about drawing fields like this is for charges is try and have the field uniform around it. Don't just draw it on one side. What I used to do, or I still do sometimes, though, in a charge, I'll actually draw like little dots on the charge. And same thing for here, I'll draw little dots on the charge and make sure a field is going in and out of each one of those dots. Because what happens sometimes, people will draw the charges, there's the positive, negative. They draw the electric field and all they draw is this, which makes it look like there's only field like directly between the charges. But there's also field all the way around the charges as well. So I will often draw these little dots around my charges nicely all the way around the shape, in order to make sure I've got field going in and out of all sides of the charge, because the field does exist all the way around the charges and charged objects. I don't really do that with my parallel plates because I know that the field we're going to be working with is in between the plates, so I don't have to worry about it as much. But it's important to realize that we do have field going all the way around them.